All right, so in this video, what we're going to do is talk about how to generate new ordinals from old ordinals. And we're going to talk about kind of two ways of doing this. One is with the ordinal successor or the successor operation. And then the other way is by taking unions. So what's our starting? We'll start with successors. So as a building new ordinals from old. And well, let's maybe first start with the successor. Well, I guess we've been using this notation, but maybe we'll actually give it I'll write it down as a definition now. So given an ordinal alpha, so given an ordinal alpha, the successor of alpha is defined as, well, it's written alpha plus 1, and it's defined as alpha union the set containing alpha. So we've seen this before, right, with inductive sets, right? We defined the plus 1 operation for inductive sets as this set union the set containing itself. But and we're kind of just following that same notation. We're going to be calling this now just alpha plus 1. So this is called the ordinal successor. So this is the successor. Is the successor of alpha. Okay, and I guess there's something to be proven here. Okay, this is a definition, so there's nothing to be proven about this definition. This is just the definition. But why are we calling it like the successor of alpha? Well, we can prove that this is the smallest ordinal strictly bigger than alpha. So what's the proposition? So alpha plus 1 is an ordinal. So that's, I guess, something that we need to check. And further is the smallest ordinal bigger than alpha. And is the smallest ordinal strictly bigger than alpha. Strictly greater than alpha. So what does this mean? So, well, what do we know? Well, alpha is going to be less than alpha plus 1. And, well, if we have any other, say, ordinal, so, and, well, for all beta, well, if beta is bigger than alpha, then it would have to be that beta is bigger than or equal to alpha plus 1. So in our line, right, so maybe alpha's right here. Alpha plus 1 actually is the very next ordinal that we're going to kind of, that's going to be on our list. Okay, so what's the proof of this? Well, we need to check two things. The first is to check that it's actually an ordinal. So why is alpha plus 1 an ordinal? So maybe claim 1. Alpha plus 1 is an ordinal. Well, how can we do this? Well, all we have to do from our previous videos, we just need to check that it's a transitive set of transitive sets. So how do we kind of maybe approach this? So proof of 1. Well, why is this thing transitive? We actually proved that this thing is transitive when we gave the definition of a transitive set. So this is transitive by previous videos. So we actually gave this argument in a previous video. And then why are all, so why is it a transitive set of transitive sets? Well, if, so this is the first thing that we need. The second thing is, well, if we have some beta that is an element of alpha plus 1, well, then it's either an element of alpha. And one thing that kind of can happen a lot, some of you'll get something you'll get used to, but instead of writing is an element of when we're talking about ordinals, a lot of times we just write less than, because, well, that is what less than means for ordinals. But if you see less than, when we're talking about ordinals, we mean is an element of. Or this is kind of, I don't know, it's just something that, some notation that can maybe be a little bit confusing, but it's good to just maybe say it out loud. So if we're in the situation where we have beta as an element of alpha plus 1, well, then it's either less than alpha, but then, well, alpha is an ordinal, and all of its elements are ordinals. And so an ordinal is a transitive set. So what does this imply? This implies that beta is an ordinal. Which also implies that beta is transitive, which is what we wanted to prove, right? So we're good in that case. Well, the other situation is, well, what if it's equal to alpha? But then we get the same exact reasoning, right? Alpha is assumed to be an ordinal, and so it's transitive. But then that's what we want. That's what we wanted to prove. Okay, so what just happened? We just argued that alpha plus 1 is a transitive set of transitive sets, and so that's one of our characterizations of what it means to be an ordinal. So alpha plus 1 is an ordinal. Okay, so the next thing that we need to do is, well, check that it's actually the least ordinal bigger than alpha. So claim 2. And how do we prove that? Well, we need to check for every single beta. If it's the case that beta is bigger than alpha, then it has to be beta has to be less than, bigger than or equal to alpha plus 1. This is what we want to check. Well, one thing that we can do is, well, so fix beta, and what we can do is assume otherwise. So assume that alpha is less than beta, but beta is not bigger than or equal to alpha plus 1. Well, we proved last time that the membership relation on the ordinals is total, so it has to be then, because we just proved that alpha plus 1 is an ordinal, it must be then that beta is an element. So beta must be less than alpha plus 1. And recall, by definition, alpha plus 1 is equal to alpha union the set containing alpha. And so the option is, well, then either beta is an element of alpha. So in other words, beta is less than alpha from this first condition. It's either an element of alpha, but that's a contradiction. This is a problem because it would imply that alpha is less than alpha, right, from this condition. Right, from right here, we know that we're assuming that beta is bigger than alpha. And so if alpha is bigger than beta, we'd get that alpha is less than alpha, which is a contradiction. Right, and you could either say it contradicts foundation, or it contradicts that alpha is a well-ordering. Right, it's well-ordered by epsilon. And well, the other situation would be that, well, beta is an element of this set, which would be the same thing that it's equal to alpha. But then we get to the same contradiction. So this would imply also that alpha is an element of alpha, is an element of alpha, which is a contradiction. So what did we just prove here? We just proved that if we took any ordinal, if that was bigger than it, maybe we should add like is an ordinal here. But if we took any ordinal that was bigger than alpha, it was actually bigger than or equal to alpha plus 1. So in other words, alpha plus 1 is actually the smallest ordinal that's bigger, strictly bigger than alpha. Okay, so that was that one. The other kind of way to generate new ordinals. So what does this mean now? Well, if we have an ordinal, any ordinal, we can always add one to it and get some new ordinal. What's another way to kind of generate a new ordinal is with unions. So with unions. And, well, I guess what's the claim? So what's the proposition? So if we have some curly f, which is some set of ordinals, is any set of ordinals. Well, then union curly f. So what does this mean? this is some collection of ordinals, and we're taking the union of all of the ordinals. Right? All the ordinals are sets, so we could take their union. So we're taking the union of all of them. And if we take the union of this collection of curly f, well, it also ends up being an ordinal. So this is an ordinal. Is an ordinal. And it's the least ordinal bigger than or equal to all of the elements of f. Further, this is the big, so this is the largest ordinal, bigger than or equal to all alpha in f. So in other words, it's bigger than or equal to all elements of f. And actually, no, I want to say it like this. Sorry, I want to say that it's the least upper bound of f. It's the least upper bound. Is the least upper bound. Or the supremum of f. So what do I mean by this? Well, it's going to be bigger than, it's an ordinal. It's going to be bigger than or equal to all of the other ordinals in f. And well, it's also the smallest upper bound of all the elements of f. So in other words, so what do we know? What's going to be the case is that for any other beta, if it's the case that, so if beta is bigger than or equal to alpha for every single alpha in f, so if this is true, well then it would have to be the case that beta is bigger than or equal to the union of f. So in other words, not only is this thing bigger than all the elements of f, it's also the smallest upper bound. So it's the smallest big thing above all the elements of f. Okay, so how do we prove this? Well, we first want to check that it's an ordinal. Claim 1. Well, why is it an ordinal? We also proved when we talked about the definition of a transitive set that if we took transitive sets and union them together, what we also got was a transitive set. So is an ordinal. Well, the first check here is that it's transitive. And well, this was from like stuff that we've done in previous videos, where when we talked about what it meant to be a transitive set, we proved one of these closure properties for transitive sets. And well, the other thing that we want to check is that all of its elements are transitive sets. Well, if we take some alpha that's in that's in the union of f, what does this mean? By definition, so by definition, what do we know? Well, there's some beta that's an element of f, such that what? Well, such that alpha is less than beta. And why am I writing less than here instead of element of? Well, because it's an element of f, we know that it's an ordinal, right? And so we're kind of being consistent with this, using less than for kind of ordinal membership. Okay, but then alpha is an element of beta, but beta is an ordinal. And so that means that alpha is an ordinal, and so alpha is transitive. So what does this imply? This implies that alpha is an ordinal, and is therefore transitive. So and is therefore transitive. Okay. All right. So that's claim 1. So this thing is actually an ordinal. And maybe it's good just with our less than notation, just write down what this means. So maybe here's like a note. I guess the definition that we gave for this thing, well, it's maybe I'll write it out like this. So x is an element of, maybe I'll write it with alpha because we know it's an ordinal. So we could say something like alpha is less than curly f. When is this true? This is true if and only if, well, there is some beta in alpha, or in f, sorry. Although F is a collection of ordinals, we don't need, it's not necessarily the case that F itself is an ordinal. Just if you union all the elements of F, you get a new ordinal. So that's why I'm using kind of membership here instead of the less than. But alpha is less than the union of F if and only if there's some other ordinal in F such that alpha is less than beta. Right? If we interpret the definition of what it means to be in the union of something in this context, this is exactly what we have. So I just thought it's good to write it down. Okay, but we proved claim 1 that this thing's is an ordinal. What we want to show now is it's actually the least upper bound of F. So what do we mean by that? Well, we need to prove that if something is bigger than or equal to all the elements of F, well, then it's actually bigger than or equal to the union of F. So claim 2. We want to check that this is the least upper bound, or the supremum is maybe another way to write it. So is the least upper bound or supremum of F. Okay, and so how do we check this? Well, let's assume that we have some element beta, or some ordinal beta, that is bigger than or equal to all the elements of F. For each alpha in F. Well, let's assume for the sake of contradiction that, well, it's not bigger than or equal to the union of F. So assume instead, let's assume instead that, well, beta is less than the union of F, right? Because if it's not bigger than or equal to it, it has to be less than it. Well, then by this note, although maybe I should have used something other than alpha, because we're kind of flipping the order. But, well, because of this, what has to happen? Because it's an element of the union of F, it has to be that there's some gamma. There has to be some gamma that's in F. Well, so that what? So that beta is less than gamma. Well, but this contradicts exactly this statement, right? That's exactly what the opposite of this is. So this is a contradiction. Okay, so what did we just argue? We just argued that not only union F, not only is like sometimes this is written, or so maybe kind of another note about this is sometimes instead of this union F, they write sup F for the supremum, right? Because this is an ordinal that is the least upper bound of all the elements of F. So maybe another note. Sometimes written sup F. So sometimes we use this notation. Okay, but what did we just argue? We just argued that, well, not only is sup F an ordinal, it's an ordinal that's the least upper bound of all the elements of F. So it's every other ordinal that's bigger than all the elements of F are less than or equal to F. Or, less than or equal to sup F. Did I say that right? Okay, I think you know what I mean. All right, so that's unions. So we can take now, if we have an ordinal, we can add one to it. But we can also, if we have a bunch of ordinals, we can find the first ordinal that's bigger than all the ones that we found the union of by unioning them all together. One thing that can happen. So maybe an example of this is, well, remember omega, that's our first kind of infinite ordinal. It's also, I guess, a set of natural numbers, but it is an ordinal. An ordinal is a set of ordinals, so we can treat this like our F and take the union of omega. So we could take the union of omega. And, well, what is this going to be? Well, this is going to be, well, 0, union 1, union 2, union 3, union, and so on. Right? Because 0, 1, 2, 3, and so on, those are all sets. Well, what do we end up getting? We end up getting exactly omega. And maybe just to kind of write this out and to see why. Well, if we have some natural number, so if we have something that's less than omega, well, then we can add 1 to it. So if we let m, maybe I'll just write it out like this. Well, then n, that's also less than n plus 1. But if you take the successor of a natural number, it's still going to be a natural number. And so it's going to be less than omega. How could we maybe give a formal justification of this? Well, what was our definition of omega? It was the least, it's an inductive set. And so what that means is that if we have an element of it, if we add 1 to it, it's also going to be an omega. But what does this condition mean? Well, we just argued that there's some element of omega such that n is less than, so some element m that's a natural number, so that n is less than m. But this is the same thing as saying that n is an element of the union of omega. And well, if you kind of do the opposite direction, you'll get the same thing. So you can kind of do the reverse directions as well, where if you have something that's in this union, well, there's something that's less than it. But if you have a natural number and you have an element, if you look at an element of a natural number, it's also going to be a natural number as well. Or you could just say something like, well, if this is the case, if we have this, by the transitivity of the less than relation, it would have to be also that n is less than omega, which is what we'd want to show. Okay. So I think that's what I want to, maybe I'll stop at that today. What we're going to do next time is kind of talk about, actually no, I maybe want to say one more thing. Normally when we take unions of ordinals, we only really care about unions of ordinals when we have infinitely many ordinals at once, right? So if we have a big collection of ordinals, we want to take the union of all those ordinals to get the one that's bigger than all of the ones that we just found. But there's nothing stopping you from, say, taking the union of, so let's say that you had alpha plus 1. Let's say that you had alpha plus 1. Well, there's nothing stopping you from taking the union of alpha plus 1. So what happens if you take the union, or the sup, of alpha plus 1? Now, this is where we need to be a little bit careful, because right now when we write union alpha plus 1, I feel like I can write it a little bit better. If we take the union of alpha plus 1, we are thinking about alpha plus 1 as a set. So what is this? So what is, so this is going to be the union of alpha, I'll write it like this, alpha with the set containing alpha. And if we think about what the union is with a collection of ordinals, it's the least upper bound of all of the elements of this set. Well, what is that going to be? Well, that's just going to be alpha. That's just going to be alpha. So this is just one thing that can happen if you take the union of a successor ordinal. The union that's an ordinal that's the successor of something, what you're going to do is go down 1. And why? Well, it's because when we think about this successor as a set, well, it's the set of all the previous ordinals. And well, the set of previous ordinals has the biggest element. Its biggest element is alpha, right? So why is this true? Well, this is because, well, alpha as a set, or alpha plus 1 as a set, this is going to be the set of 0, 1, 2, and it's going to go all the way up to alpha. It's going to have some biggest element alpha. And so if we union all these together, what we're just going to be left with is alpha. Okay, so I'll stop there. What we're going to do next time is talk about like the different types of ordinals. So there's kind of 3 main types. There's like 0, right? That's a type of an ordinal, I guess. Then there's successor ordinals and what are called limit ordinals. And so afterwards, what we're going to do is talk about, well, ordinals now are well orderings, or they're all well orderings. And so we can talk about doing induction and recursion on ordinals. So we're going to be, I guess, working, that's our short-term goals to talk about those things. So I'll see everyone in the next video.